Hello students, so continuing our lectures on transport phenomena. Today we will start with the concept of Mach number. Mach number is the ratio of the speed of a body, moving body, divided by the speed of sound. Speed of moving body or the speed of sound. So let's write them as equal to speed of a body divided by the speed of sound which is 330 meter per second. Meter per second. This is the speed of sound. So this is considered to be the Mach number. Now we have different categories of sound based upon the Mach number. So let's call this Mach number as M. So if M is less than 1.0, we call the sound to be subsonic. If the Mach number is exactly equal to 1, that is the speed of sound and the speed of the body are equal, then we call the sound to be transonic. If the speed of sound is more than 1, we call it to be supersonic. And lastly, if the speed of the Mach number M is more than 5 times, more than 5 times the speed of sound, then we call it to be hypersonic. Usually the aircraft which travels, it has much higher sound, say close to 200. You can imagine what speed the aircraft might be traveling. Now, as the aircraft travels with high speed, so aircraft traveling with a high speed, the surrounding air of the aircraft gets compressed. So if this is the aircraft traveling with high speed, the surrounding air in the region, this region, it gets compressed. we know that air is a compressible fluid. For air, is not a constant. Okay, it changes. So del rho by del T, this is not equal to 0. But in case of water, water is considered to be an incompressible fluid. So this is equal to constant, and therefore del rho by del T is equal to 0. So this case is not applicable here, because in aircraft we are mainly concerned with the movement of aircraft through air. Okay. So the equation of continuity, if we move back to the equation of continuity that we have discussed previously, so equation of continuity is del rho by del T plus of rho V is equal to 0. Okay, this is basically the conservation of mass. Now, what we can say from this equation is that the velocity will be a gradient of a scalar. Or we can say that V bar is equal to minus gradient of phi, the scalar quantity, and from scalar potential. And from here we can also say that del square phi is equal to 0. So this is the Laplace's equation for irrotational flow. Laplace equation of irrotation flow, and it can be solved for various coordinate systems like Cartesian coordinate system and spherical coordinate system, cylindrical coordinate system. So that will be taken up in due course. Now let us move to our discussions on the movement of aircraft at a very high speed. So an aircraft is moving with a very high speed as previously told, and as it moves, so it creates waves of large amplitude. So here waves are created which are having very large amplitude. Waves a very large amplitude. So there will be regions of high pressure and there will be regions of low pressure. And the regions of high pressure of high pressure they will move faster compared to the regions of low pressure. So due to this difference in speed of different regions of air, say there will be regions of fast pressure, there will be generation of something called shock waves. Which are again, these shock waves will be again, as you can see from the diagram, will be sawtooth, will have a nature of sawtooth. By sawtooth we mean that it will be like this, sawtooth. So sinusoidal waves have the nature like this, whereas sawtooth waves have very sharp amplitude, so we will move like this. So the waves moving in front, or due to the air pressure, they will have a sawtooth nature. Okay, so when a macroscopic wave, as in this case, it again approaches a sawtooth character, it has a sawtooth character, it becomes a shock wave. So this is what happens, this is how the shock waves get generated. Okay, now as there will be a shock wave similar to that, or in relation to that, there will be a shock front. This is the shock front. So we will have a difference in pressure before the shock front and after the shock front. This shock front will be characterized, will have a back and forth pressure. That means back and forth pressure. It will be having velocity u, pressure P, and density rho, the shock front. But apart from that, this region before the shock front will have a cross-section area A2, pressure P2, and density ρ2, and this region A1, P1, and ρ1. Okay. Now the rate of mass flow into the front should be equal to out of that. So the front region of the shock waves and the rear region of the shock waves, they will have the same rate of mass. So that means if you consider these two regions, for these two regions, although the shock waves are having constant velocity, pressure, and density, the mass flow from this region to this region will follow the equation of continuity, that is rho 1 p1 u1 rho 1 u1 will be equal to rho 2 u2. This is the equation of continuity. Now the max speed, if you consider the max speed in these two regions, in the first region there will be a max speed m1, and corresponding to the second region there will be a max speed m2, where m1 would be simply equal to u1 by c1 if c1 is the velocity of sound in the region 1, and similarly m2 will have max speed of u2 divided by c2. Okay. So m1, let's write this one again, and m2, these are the two max speeds at in between the shock front, and this is the shock front in between, and the aircraft is traveling along this direction. So if m1 is equal to m2, both the Mach numbers are equal, then again the pressures will also be equal, and the density of the air in the two regions will also be equal. So no shock waves are generated at all, and the disturbance progresses with a normal sound velocity. However, if m1 is greater than 1 and m2 is less than 1, this is m1 and this is m2, so it means that the aircraft flows at a supersonic velocity on passage through a shock wave. So as the aircraft flows, it attains a supersonic velocity on passage through shock waves. Now passage of a shock front in an ideal gas. So as the shock front increases, its shock front moves as the aircraft moves. There is an increase in temperature, there is an increase in pressure, and there is an increase in density as the shock front or the aircraft moves in ideal gas. Okay. However, the one thing that gets reduced is m. The Mach number, however, gets reduced. And if the speed of the aircraft is very high, that means maybe, as I've told, if the Mach number is more than 200, then the shock is very strong and the temperature rise will be very high, and it may even change the value of this derivative, the ratio of the two specific heats. This value may also get changed due to this high moving spacecraft, high velocity spacecraft, and it may lead to dissociation and ionization of the air or of the gas. There can be dissociation and there can be ionization of the gas in of the air in front of the aircraft. Now, how much is the shock wave? That is determined by simply the ratio of P2 by P1. If you take the pressure difference in the two regions before and after the shock wave, movement of the shock wave in front of the aircraft, then it will give you the shock strength. And the dissociation of the air it normally takes place at around 3000 Kelvin, and the ionization takes place around 5000 Kelvin. So this amount of heat may be generated due to the motion of the shock wave or the motion of the aircraft. So if we plot temperature versus Mach number, so you can have two different plots, A and B, and it has varied from Mach number 2 to Mach number 60. So A is for the ideal one, when there has been no dissociation of air taking place, where B is when there is dissociation and ionization. Okay, so by dissociation and ionization, what happens is that the air sometimes tries to compensate for the increase in temperature taking place, and this occurs at around 60.